All right, let's get right into it. Have you ever stopped and wondered what you're really made of? Or, what your desk is made of? Or the air you're breathing? If we could zoom in way, way past what our eyes can see, past the cells, you'd find the atom. And today, we're going to crack the code on this tiny little thing that builds our entire universe. So, here's our game plan. First up, we're going to peek inside the atom to meet the three particles that make it up. Then, we'll figure out how each atom gets its own special ID card. After that, we'll meet its slightly different family members, called isotopes, and tackle a real head-scratcher. How do you weigh something you can't even see? We'll do a bit of math to find its average mass. And finally, we'll find out where those super important electrons actually live. Let's do this. Okay, first section. Let's start with the absolute basics. What's an atom actually made of? Well, it's not just one thing. It's actually a team of three incredibly tiny particles. We call them the subatomic trio.
Okay, so right at the heart of the atom, you've got this dense core called the nucleus. Packed inside are two key players, the protons, which have a positive charge, and the neutrons, which, as the name kind of suggests, are neutral, no charge at all. Now, both of these guys have a relative mass of about 1. Then, zipping around way on the outside, you've got the tiny electrons. They've got a negative charge, and they are so light that their mass is basically negligible in comparison.
Now, to give you an idea of the scale here, because it's pretty wild, imagine an atom is blown up to the size of a giant football stadium. The nucleus, right, where almost all the mass is, that would be like a single marble sitting on the center spot. A marble. The rest of it is just vast, empty space. That's where those electrons are flying around. Kind of blows your mind, right?
So you might be thinking, with all these positive protons and negative electrons flying around, why aren't we all getting constantly zapped with electricity? Well, the answer is super important. It's all about balance. You see, in a normal, neutral atom, the number of positive protons is exactly the same as the number of negative electrons. They perfectly cancel each other out. Positive 1 meets negative 1, and boom, the overall charge is 0.
Okay, moving on. Section 2. So we know the building blocks, but what makes an atom of gold different from, say, an atom of oxygen? It all comes down to two key numbers. Think of it like the atom's own personal ID card. The first number, and honestly this is the big one, is the atomic number. We use the letter Z for it. And it's super simple. It's just the number of protons in the nucleus. That's it. But here's why it's so critical. This number is the element's identity. Every single atom of carbon in the entire universe has exactly 6 protons, no exceptions. If an atom had 7 protons, well, it just wouldn't be carbon anymore. It would be nitrogen. It's the ultimate identifier.
All right, the second number you need to know is the mass number, which we call A. This one's also pretty straightforward. It's just the total count of the heavy guys in the nucleus. So that's your number of protons plus your number of neutrons. And since the electrons weigh next to nothing, the mass number gives you a really good idea of the atom's total mass.
So, of course, there's a neat way to write all this down. The mass number, A, goes top left, and the atomic number, Z, goes bottom left. Let's take sodium here. We see 23 on top and 11 on the bottom. This tells us its mass number is 23 and its atomic number is 11, meaning it has 11 protons. So, quick quiz. How many neutrons does it have? Well, if the total heavy particles add up to 23 and 11 of those are protons, you just subtract. 23 minus 11 gives you 12 neutrons. See? Easy.
All right, section 3, the isotope family. Now, you'd be forgiven for thinking that all atoms of, say, carbon are identical twins, but that's not exactly true. They're more like siblings. Part of the same family for sure, but with some small differences. And that brings us to the idea of isotopes.
So what on earth is an isotope? Here's the key idea. Isotopes are atoms of the same element. That means they have the same number of protons. Their atomic number is identical, but they have a different number of neutrons. And if the number of neutrons is different, that means their mass number is also going to be different. Same identity, different weight.
Hydrogen is the perfect example. Check it out. Every single hydrogen atom has 1 proton. That's what makes it hydrogen, but the most common type, protium, actually has 0 neutrons. Then you've got deuterium, which has 1 proton and 1 neutron. And then there's tritium, with 1 proton and 2 neutrons. See, all of them are hydrogen, but they have different masses.
Okay, so why do we care about this? Well, here's the cool part. Chemical reactions?
They're all about the electrons. And since all isotopes of an element have the same number of protons, they must also have the same number of electrons to stay neutral. And that means they have pretty much the exact same chemical properties. They react the same way. What's different is their physical properties. Because they have different masses, things like their density might be slightly different.
Next up, Section 4, weighing the unweighable. I mean, think about it. How do you possibly weigh a single atom? The number in grams would be ridiculously small. It's just not practical. So scientists got smart. They decided, instead of finding its actual mass, let's just compare it to something else. They created a relative scale.
And this leads us to a question that trips up a lot of people. We just said the mass number is a count of whole particles. So why on the periodic table does it say chlorine has a mass of 35.5? You can't have half a neutron. What's going on? Well, the answer comes back to that relative scale. Scientists picked a reference point, an isotope called carbon-12. They said by definition, one atom of carbon-12 has a mass of exactly 12 units. Everything else is measured against that. So let's clear this up once and for all, because this is crucial. The mass number is just a simple count. Protons plus neutrons in a single atom. It's always a whole number. For chlorine, an atom can have a mass number of 35 or 37. But the relative atomic mass, that's the number on the periodic table, is a weighted average of all the different isotopes found in nature. And because it's an average, that's why you get decimals.
All right, Section 5. Let's talk about calculating that average mass. I know, weighted average sounds a bit complicated, but I promise the calculation is actually really straightforward. Let's just walk through it.
We'll stick with chlorine. So out in the world, about 75.4% of all chlorine atoms are the lighter chlorine-35 isotope. The other 24.6% are the heavier chlorine-37. So to get the average, we just take the mass of each one and multiply it by how common it is. So that's step 2. We do 35 times its abundance, 0.754, and we do 37 times its abundance, 0.246. For step 3, you just add those two numbers together. And when you punch that into a calculator, what do you get? Boom, 35.5. And that is the number you see on the periodic table. So remember, it's not the mass of one specific atom, it's the average mass that takes into account the natural mix of all its isotopes. Okay, final section. We've spent a lot of time talking about the nucleus, but now we're going to zoom out and look at where all the chemical action happens. We're talking about the electrons, and they don't just fly around wherever they want. They have very specific addresses. We call these addresses electron shells. Think of them like layers of an onion around the nucleus. The first shell, the one closest to the center, is tiny. It can only hold a maximum of 2 electrons. The second shell out is bigger. It can hold up to 8. And the rule is simple. Electrons always fill up the shells closest to the nucleus first. So take sodium. It has 11 electrons. The first 2 go into that first shell. Now it's full. The next 8 fill up the second shell. That's 10 so far. The last 11th electron has to go into the third shell. So we write its arrangement as 2, 8, 1.
And listen, this orderly arrangement, it isn't just about keeping things tidy. That one single electron in sodium's outer shell, that's the key to everything. It explains why sodium is so reactive, why it bonds to make things like table salt. Really, the arrangement of these outer electrons dictates pretty much the entire world of chemistry. So how exactly does that work? Well, that's a story for our next explainer. Thanks for watching.